Power supplies is the application of diodes, right? One application. They're really, really neat. We can make them do logic. We have what we call diode logic gates. We can make them do logic, but that would be when or if you take the digital class. If you're in the ILT course, you'll take the digital. AUT, I think it's an elective. So power supplies, and of course DC power supplies, but normally we use the term power supplies. We're talking about that device that takes AC and converts it over to DC, right? You understand that? And of course, normally, what do we have that makes up a power supply? First, we got to have the original source of the power, right? And what normally comes next? What normally comes next? What normally comes next of the parts of a power supply? Each one of them has a function. What comes next? That's a plug. Does it look like a plug? Yeah, a transformer comes next. Good. Not always, but probably 99% of the time. And then the transformer feeds the what? What comes next? Rectifiers. Now, what's the function of the transformer? Could, but this guy actually sets the output voltage if you think about it. So this is the source of the power up here, but if we need a higher voltage than what the power company gives us, then we use a step-up transformer, and we make sure we have more than what we need, right? Everybody understand that? Rectifiers, what does it do? So this converts AC to pulsating DC. And then this is where we're at so far. But before long, we'll come up here and add this. And what's the function of the filter? This guy converts pulsating DC into unregulated DC. So what do we mean by regulated DC? If you don't know what regulated DC is, you don't know what unregulated DC is. So what is regulated DC? Huh? So either we're not studying or I'm up here just talking to myself when we talk about this. So you're going to have to, say, do I want to know this or I don't want to know it? If you don't want to know it, you probably need to find yourself a different trade. Or you can just come to school and sit here and listen to me talk and then go home and then, not want to get a career in this kind of stuff. We're trying to learn this stuff. So what is regulated DC? If you don't understand regulation, you're going to have all kinds of problems. We use that term all the time, even in manufacturing, in automated systems, regulation. So regulation means we're going to try to maintain a constant output even though things change. A pretty good example, it's not perfect, and no regulator is perfect. We can't say constant because there's no such thing as a perfect regulator. That's just like there's no such thing as a perfect cruise control on a car. Your cruise control is a regulated system. So your cruise control, what does it try to do? It tries to maintain a constant speed with varying road conditions. That's what it tries to do. I'm laughing. We was going out to Dallas, Texas to go to a wedding, and they had an ice storm come through. My dad, we were in two different cars. My dad was going, and it started icing, and he didn't take off his cruise control, and he went across the bridge. And by George, that car tried to maintain a constant speed. So what happened? I mean, the car just started spinning. He almost lost it. He was lucky. It can't maintain, and you can see it. So when you go if you go up a hill, the spot drops down a little bit, right? And when you go down the hill, it goes up a little bit. But it's pretty dang close. It's pretty good. But there's not perfect. We don't have. So what it tries to do, what unregulated means, if the load changes, the output voltage changes. If the input voltage changes, the output voltage changes. So the output voltage would not only vary with input voltage, it would also vary with load. So it means if I took this power supply and I got it here, and then I went out over to then I go over there to A build, and their AC is different than our AC. It's close. The voltage would measure different. Now, if it's regulated, that means I can take this sucker right here and I can plug it over here. I can take it home. I can plug it in. I can plug it in A building. I can plug it in D building. All these buildings, even though they've got their own transformers, I can come over here, and this is a regulated device. It's 20 volts. And it's going to measure about 20 volts no matter where I go, right? You understand? Everybody understand that? I could come over here and I could do all kind of stuff with my computer. I could be playing music. I could be doing all kinds. So right now I'm not using the speakers. As soon as I use the speakers, my computer's going to pull more current. But the output of the power supply is going to stay constant, even if I take the battery out of this thing. Now the battery acts like a pretty good filter. Y'all understand that? In fact, this is what your car uses. Your car uses that big old 12-volt battery out there as the watt, as the filter. It does a really good job. So the filter, what it does is convert a pulsating DC into unregulated DC. Is this going to be good? Well, it depends on what determines where you stop at. So the less stuff we put into a power supply, the less expensive it's going to be. What determines where you stop at? Load. What type of load are you connecting to this thing? If you're connecting an electronic load, you're going to have a regulated power supply. If you're connecting a light bulb, or you're running a heater or something like that, or a DC motor don't need regulated voltage. So it all depends what load you're trying to run with your power supply. And of course, eventually we're going to get to a regulator. And then over here we'll have our regulated DC. So right now we're in here. We're looking at this just a little bit. We put a capacitor across this last class and saw what the capacitor did. And it no longer pulsed to ground, right? You understand that. So this is the basic makeup of what we refer to as a linear power supply. Yeah, when you get into switching power supply, it's going to be different, but I'll give you a little head on that. So we start off with rectifiers. Then we go to an oscillator. Then we might go to a transformer. And then we might go to filters. Then we'll go to an output. Then we'll come back here and we'll take this and we'll have what we call feedback, which controls the oscillator, which is pretty good. And this is what we call a switching power supply. And we'll look at this just a little bit. The problem with switching power supplies, what did I tell you the problem with switching power supplies? They're very efficient. They're electrically noisy. So they cause they've caused problems with the power grid, but over time they've learned how to filter. They actually filter the input. So normally what they do is right in here now, what they'll do is they'll have a pre-filter, because these guys here cause Cat AC, they call spaceships. They call weird stuff in the power grid, but they're extremely efficient, which means if this was a linear power supply, it'd probably be a lot bigger. This is 20 volts at 3.5 amps. So the transformer would be huge, and the filter capacitors would be huge. This would probably be maybe 5 times bigger than this if it's a linear power supply. But this is a switching power supply. Switching power supplies are harder to design, and they're hard to fix because they depend on feedback. So if it don't have feedback, it's supposed to start oscillating. It's supposed to have what they call a startup circuit, because you don't have any feedback to start up. So you got to start up, and if it don't start, you don't get feedback. You don't get feedback, you don't get regulation. But you don't get feedback, you don't get startup, right? You understand? So you get in what we call a troubleshooting loop, where everything measures for it to start, but it just don't start. So these guys are hard to troubleshoot. So normally these guys are consumables. So right now, if this thing goes out, what am I going to do? I'm going to try to fix it. I'm going to throw it away. But if the power supply goes out in the trainers, I'm going to fix it. Because why? They're a linear power supply, and they're easy to fix. They're not extremely difficult once you get a little troubleshooting under your belt. We're going to look at that in a minute. So there was something neat that the book taught that I haven't noticed before, but it was pretty neat. But we'll look at that in a minute. First of all, let's come over here and we'll start off with a transformer. And we'll step down. So normally a step down transformer, you're supposed to draw the secondary windings less, but you'll see most people draw them the same. It's no big deal. And then normally you have what type of core you have. And we have what we call a laminated core. Let's see if I can find one of these that's... So this is a laminated core. This is a bad transformer. You can't really see it from here, and it's got to be laminated. So I'm going to take off what we refer to as the mu shield. And what this does, it just helps prevent the transformer from making a lot of electromagnetic interference. So all I'm going to do is take off the outside shell so we can look at what we call a lamination. And so you just can't take a bunch of wire and wrap it around a chunk of metal and to get a transformer. So what we're trying to do is we're trying to concentrate the magnetic field between the two windings. So this is the transformer. This is the in fact, this is the actual transformer that came out of the train. And you can look in and you can see the windings. And this is what we call an E-core, because you look, it's got another chunk of metal that comes through here, so it's basically got the shape of an E, right? See that? Like both your primary and secondary are wound on top of each other, but the core has to be what we call laminated. And I'll pass it around and I'll show it. But we got hundreds of little tiny individual plates in them. And what they do that for is to prevent the current being produced inside each one of the chunks of metal from adding together. So what do we need to magnetically produce a voltage or electromagnetic force? What do we need? Can we talk about that in here? And we talk about this, what 3 things do we need? No, we're trying to produce it. We're trying to produce the source. We're trying to produce a voltage electromagnetically. What's the 3 things we need? So what 3 things are required to produce a voltage electromagnetically? We're trying to produce an electromotive force using magnets. What 3 things do we need? So nobody in his old class don't know. What do we need? Okay, good. We need a magnet. Wait, takes me a little while to write. What do we need? Where's what we're trying to produce? We're trying to produce how does my generator in my car work? What? Yeah, well, we need at least one conductor. That is a conductor. Huh? That's what we're trying to make. We're trying to make. So this is like I say, what's required to make a cake? And y'all say it, a cake. What do I need to make a cake? You need a cake, Rich, to make a cake, you know. What do we need? So what do we need? This is the recipe for your alternator out there. Your alternator has a recipe. Your alternator makes electricity. We need motion. We don't need a core. A core concentrates it and makes it better, but we don't need a core. So literally, I can take a magnetic field and I can move a conductor through it. And if I was fast enough, I would see a pulse come out of it. That's all it takes. Huh? What determines the amount of EMF? Go right down the line. What about the magnetic field? What about the magnetic field determines the amount? I got a big old magnet in here, and I got a little old tiny magnet, and the little old tiny magnet would produce a bigger EMF than the big magnet. So you can't say the size, right? You understand? Strength, good, yeah. Yeah, if we think about it, each one of these windings, when I move a certain direction, each one of those windings is basically acting like one of those. It's just that we're constantly doing what? Turning. So what I need to do is if I come over here and I wind these things up, and I wind them in the same direction, we end up with that right there. So every one of those little windings would produce a little tiny EMF, but if we wind them in the same direction, then those little EMFs that they produce are series 80. Series 80 DC sources add together. So what we do is we just come over here and put a bunch of loops. So the number of conductor loops, or coils. Well, coils are made out of loops, so loops will be number of loops in our conductor. And what would be the next thing? Huh? We're dealing with the motion. The motion. Huh? The speed, yeah. So the speed of the motion. So the faster I can move it through that conductor, the more EMF it's up. This is what's required. But when I went and got the transformer, so you said what? 169. Out over here across that little resistor? I would say that has a 0% probability of being correct. But it's no big deal, right? I mean, now this is in class. You get on tests and you put that down. Yeah, but that's not the average voltage. That's not the average voltage. So what you did is you took this right here and converted it to VP. And you came up and got what, Courtney? That's 169 volts right there. That's not on the other side of that transformer, right? That transformer is a step down transformer. So right off the bat. So see what you did wrong? So what did you do? You just stopped by converting VP. Well, first of all, we got to figure out what we're going to get on our secondary. We got to figure out what we're going to get on our secondary. Should be 30 volts, or it could be 169 divided by 4. I mean, either way is fine. We got to get to this right here. We got to get to that right there. That's what we got to get to. Right? You understand it? And VP is, what's the formula for VP? This is one of those formulas I shouldn't get you. What's VP? Voltage RMS divided by 0.707. That's that right there. So you can do it on the primary and then divide it by 4, or you can divide by 4 and then do it on the secondary. It's your call. Right? You understand that? But we got to get to VP. So I could start right here and I can say, okay, VP would be equal to 120 divided by 0.707. So VP would be equal to what? Is that 169? Okay, 169.7. In this class, when you get out in the real world, you're not going to round. I mean, you would probably do that. Here, we're going to round to 1 decimal point, right? And then I got to calculate VP that we get on the secondary. That's the next thing we're going to do. So I take 169.7 and I would divide it by 4. And that would give me VP on the secondary. So what would VP on the secondary be? What's that? Okay, that's one way we could do it. And it's basically, you know, up to you. Or I could come up here and I could say 120. I could say 120. I could say VRMS, V on the secondary. This is not P. Would be equal to 120 divided by 4. What does that give us? That gives us 30. And then I could say the peak secondary would be equal to 30 divided by 0.707. And we should come up and get the same thing. 42.4. So that's what we're saying. You can do it either way you want to. It's just that you got to end up with 42.4. Right? Go ahead, Court. We don't put DC on transformer. We're doing it, and we're talking, and the lecture we're doing is AC to DC supplies. That's what we're lecturing. DC is over here. We ain't got there yet. We can't get to over there till we flow through this thing, right? You understand? Okay, so what would be the next thing I would do? Next, we're going to come up here and calculate what we call V peak out. And this is out of the diodes. So I'm going to say 42.4, and I'm going to subtract 0.7 of a volt. We're going to do this for anything under 50 volts. So what do we got? Uh, 41.7 volts, right? And this is still peak. And then I calculate my DC, volts DC. And now this is an average. Everybody understand that? Then I'd say V peak over pi. V peak out, 41.7 divided by pi, 3.14. And then we multiply our answer times 2. No, we're not going to multiply by 2. Sorry. This is half wave. We lose the times 2. Times 2 is for full wave. And this will be DC. So up here, you're supposed to be putting V peak up here. Down here, you just put volts because this is and we put, yeah, this is volts. That's what we're dealing with, volts. Huh? I didn't get a last part. I don't have a calculator right. This is, I got a 2.2K over here. I don't have a 1K. I'll go get a 1K while y'all doing this. So, 120 volts over here. My transformer is a 17.5 to 1. What output should I expect? What you got, Courtney? Nothing? What you got, Courtney? Huh? Nothing. Charles? Nothing? Luke? Scott? Huh? So, this is one we have wired up. We have one wired up here, so we'll look at this there, goodwill. What's that? So we'll come up here. First of all, I'm going to figure out my RMS on my transformer. So I'm going to say 120. I'm going to divide it by 17. What did I say? 17.5? What's that? 6.8 is what it is. It's in there. Wait. 6.8, 6.85 or 6.9. Okay, then I'm going to calculate the peak on the secondary. And then I'm going to say 6.9 divided by 0.707. Does that give us? What's that? 9.6. Oh, okay. Yeah. Then we calculate what we call V peak out, which is what we're going to call it. This is out of the diode. This is going to be 9.6 minus the forward voltage drop of the diode, which should give us around 9.2 volts, right? Okay. Oh, yeah, I can't subtract. 8.9. Oh, just making sure you're there. Then I would come over here and I would say volts DC. DC would be equal to 8.9 divided by 3.14. So what does that give us? DC, volts DC. Yeah, this is what we're getting out of this thing. So over here we're dealing with what? Here we're dealing with AC. Down here, what do we get out of it? DC. And what do we get, Brandon? 2.9 volts. Okay, so what wattage resistor do I need out there? So what's the three things that resistor? Every electronic component is rated in certain things, and that's something you need to know. Or if you don't know that, you can't even shop for them, right? You understand that? So what's the three things that we're looking for on a resistor? We're looking for what? Three things. What's the three things? Huh? Tolerance would be way down here. But you're right, that's one of them. What'd you say? The ohms value of it. What's the next thing? It's very, very important that people don't think. Huh? I taught a class, we used to teach a class in power supply design. We just don't have enough time to do it. And what they did during the semester is they built a power supply that was there. So they bought the parts and that was the project for the power supply. And then what was doing is we were trying to figure out specifications on the power supply. And the spec says put 100 ohm resistor out there. And more than one person come up and said, Rich, something's wrong with my power supply. It keeps burning my resistor. But what they didn't do, they didn't even figure this second very, very, the first two values are the most important. The tolerance is no big deal. But you got two things that are extremely important about resistors. And what are ohms and, guys, if y'all don't know this, y'all in trouble. So resistors are rated in ohms, they're rated in watts, and then they have a tolerance. If you don't know that, you're in trouble. Because you couldn't even buy it. You go up here and say, I want a 100 ohm resistor. The first thing I'm going to ask you is what watts you want. Right? You understand? Don't understand. This is important. If you don't understand this, you can't even buy a resistor. Either you're going to spend way too much money, go in there and say, I want a 100 watt resistor. They say, well, what wattage you got? You say, well, give me the biggest wattage you got. And they bring a 1 ohm resistor that's this big and it's round. I'm going to charge you $100 for it. You can say, that's too big. Now all of a sudden they think, you're not very smart, right? You understand? So if you don't understand how to buy parts in your trade, my youngest granddaughter, she brought, I don't know what she brought. She had tires that were wearing out. And all four of the tires were different sizes. She went out, she needed a tire. She just went out and got a tire, a used tire. And so we had three, and she was wondering why they wore out. So we bought her 4 new tires for her SUV. But she didn't know. All she knew was tires, right? I need a tire for my car. There's a lot of stuff that tires on your car, right? You understand? So I'm laughing, but that was true. So what these people were doing is when they needed a 100 ohm resistor, they just went in there and got a 100 ohm resistor and they put it across their power supply. Put a 100 ohm resistor across, 15 volts. What would be the wattage? V squared over R, right? Yeah, so 15 volts squared, squared divided by 100. That's 2.25 watts, and they were putting a little quarter-watt resistor up there. What was it doing? It burned them up fast as they could put them in. And they was coming up and saying, something's wrong with my power supply. It keeps burning up resistors. So that's what we need to do. I'm going to put a 1K resistor up here, by George. I better make sure 1K is no problem. Right? Brown, what would that be? What would the color code be? But good gracious, he expects us to know stuff that I'm supposed to know. Brown. Good. Black. Two zeros. Brown, black, red. So I got that. I got a brown, black, red. I got it right here. But now I'm fixing to fire this puppy up, and I got to see if I'm gonna burn this up. Right? You understand? So what would be the wattage rating on that? Well, we know our voltage is around 3 volts, so 3 squared divided by 1K, right? So 3 squared divided by 1,000 is 9 milliwatts. I got a quarter watt resistor, so I'm fine. So we're okay. So let's measure our voltage and see what we got. We're expecting around 3 volts, and we'll see if we got it. So I know what to expect now, right? I mean, if you don't know what to expect, of course, there's very little that can go wrong with a half-wave rectifier. What would I get out if the diode opens? If the diode opens, what would the voltage I'd get out? If the diode opens, what voltage would I get across my resistor, which is my output voltage? Let's see, that diode is in series with the output. So if the diode opens, there's no current path to the resistor. There's no current flow through the resistor. The resistor wouldn't drop any voltage. So what would the output voltage be? Z0. Now you might pick up a little ghost voltage there, but it's going to be nothing, right? What would happen if the diode shorts? What would happen if the diode shorts? What would my DC output measure? Huh? So I'm gonna put my meter on AC. Okay, so I got my meter on AC. Let me put it over on the camera. Okay. And so I don't have it hooked up to anything. I got it on AC. I'm gonna put this sucker in this wall outlet right here. Okay, and it's measuring 113 volts. Y'all see it? I'm gonna put my meter on DC. What does it measure? I'm gonna put my meter on AC. What does it measure? So why does it measure 0 on DC? And why does it measure 115 volts or 14 volts on AC? What's the DC average of a cycle? 0. So what would my meter measure? What would my meter measure if the diode was shorted? It measures 0. So it measures 0 if it was open. It would measure 0 if it's what? Which is no big deal. So what would you do next? So let's check and see. So it's not shorted. We'll short it. I mean, we can short this. It's not going to hurt anything. We're going to have to be real careful on our full wave rectifiers, but this is no big deal. And then my RMS value, I'm going to be putting, so let's put it on DC, put it on 20 volts, and let's look across our load, make sure everything's powered up. Oh my goodness, can y'all see what it says? Can y'all see it now? What did we calculate? 2.9? 2.95. That's pretty good, considering we've used a lot of approximations. I'm going to open the diode. So here's the diode open. Here's the diode's open. And what is it? Wait a minute, it's not open. Here the diode's open. And it measures what? 0. And I don't have a piece of wire to short it. Yes, I did. So I'm going to come over here and just put a wire across the diode. It's not going to hurt the diode. Do I have room? Okay, so the diode's shorted. And I'm going to measure my DC output. And what does it measure? 0. Okay, so you measure 0 on the output. What would be the next thing you would check? So normally when we troubleshoot, we start on the output. And so I came over here and I put my meter right here. It measures 0 volts. Where would I go to next? Huh? Where would I go to next? Measuring voltage. All we're doing is checking voltage. I'd go to the source. So I'd go here. So what we do is we move from the output back toward the input, right? You understand? Now I know right here, I'm supposed to measure what right there? On that secondary of the transformer, am I supposed to measure DC or am I supposed to measure AC? I'm supposed to measure, AC. On the transformer, we're supposed to measure AC. So I'm going to come up here, I'm going to put my meter right here, I'm going to put it on AC, and I'm going to measure the secondary of the transformer. So here's the secondary right here, and it's measuring 6.8. I'm sorry, 7.2. You know it's a little high, right? Okay. So on my output, I get 0. Right, you understand that? And of course, if I look at the output now, I see that the diode is shorted, right? But it don't make any difference. I have 0 volts on the output. I got AC on the input. What's got to be bad? And of course, you got to remember over here, you're going to put your meter on what? AC. Over here, you're going to put your meter on what? DC. Over here, I measure 0 volts. Over here, I measure 7.2. What's bad? Diode's bad. Diode's got to be bad. It's shorted, of course, but the diode's bad. Now, of course, if you got a shorted diode in a full wave rectifier, it's going to blow a fuse, if you have a fuse. But your trainer's got a fuse in it, and then the power supply that I have is fused. So see, oh, I'm sorry, it's a fuse. So running an unfused, it's in the primary. Running an unfused transformer is not very smart, right? Okay. Because in a full wave rectifier, oh, that's my magnet. I can't find the other side to it, which I need to find it. Let's try to pull them apart. We can do that. These are two magnets. So Brandy was talking about the size. I'm going to put these two magnets together and try to pull them apart. I'll go get some big ones too. You'll see the big ones can pull apart real easy. But these guys right here, these are what they call rare earth magnets. So if the diode shorts, we get AC across the load, right? You understand? If the diode opens, we get nothing across the load. And how do we check to see if how do we check a diode? What do we use to check a diode? So how do I check if the diode's good or bad? Well, we can turn power off the thing. So we never put an ohm meter in. So this is another thing that we got through talking about. Not supposed to. Well, we do check. We check with power all the time. I just check with the power, but what we're going to use on our meter, we never check with the power. So how do we check a diode? I'm listening. Who's not here? I'm going to have somebody else in this time. Huh? How do we check a diode? With our meter. So I go over this long, elegant spiel about how to do this last class, and then I come back to next class and ask the same question, and nobody knows. Yeah, use diode scale. If you don't, you can use just a high ohm scale. We put a diode scale. First of all, we try to check it in the circuit. And so what I'm going to do is I'm going to forward bias it. Let me get this other diode out. This is halfway. Show y'all some problems. And we'll look across it. And so it's measuring about 7/10, if I can get into it. Right? Then when we reverse bias, it should measure open. Oh, it's not. So if it checks bad in circuit, what's the next thing you're supposed to do? Something's going on, so I'm going to isolate one lead, and then we'll check it out here. So this is reverse bias. This is forward bias. This diode looks bad. Oh yeah, I need to use this one. It's measuring like an LED. So this diode measures that. So it's silicon, so what should it measure forward bias? So when we forward bias it, what should it measure? Silicon diode. When I went through A school in the Navy, I become they call them aviation electricians, but we had to know a lot about city conductors. We had a test. We went through phases. I can't remember how many weeks the phase was, but it was 52 weeks of school. About a year. I was a year of school. And in every phase, you'd take a test. If you failed it, then you can take it one more time. And then after that, you lost your rate. I said you was going to be scraping barnacles off the hull of a ship in Adak, Alaska, is what they said. So they gave an incentive to learn that stuff, right? So what I'm saying, guys, this is your trade. You're not going to run your trade if you just come in and set on a class and then you go home and just forget about it. You need to go back and review what you learned that night. So right now nobody's passing this class because we went over this stuff last class, and then we come back and nobody sounds like we're going back to day one, huh? About 0.7, it's going to be around there, 4 buys. And these are silicon diodes. Rectifier diodes are, we got some, in one of the labs, this is the one we should have done first. We'll do this once we finish, if we can get to the lab. We're not going to do lab unless y'all can understand what you're doing in there, right? You understand? So we measure this, it's measuring 1.195 volts. And then I come over here, it's measuring way high. I come up here and get this guy, and I forward bias it, and it's measuring about 0.6 of a volt, which is usually what they measure. And then I'll come up here and swap it around here. So this diode right here is good. So there's a problem with this diode right here. When I had my scope going a while ago, I noticed something different, but I didn't take them out and check them. So if a diode measures bad in circuit, don't assume it's bad. You need to isolate it, right? Normally what we do is we take one lead out of the circuit. That way we can isolate. Any component in a circuit, an electronic circuit that checks good in circuit, we assume it's good. If it checks bad in circuit, then we isolate it, and then we check it again, unless it's obvious it's bad. Sometimes that's one of your troubleshooting. What's the rules of troubleshooting? How do you troubleshoot? What's the procedure for troubleshooting? What's number one? Randy, know how it works. That's number one. These are Richard's rules of troubleshooting. They're really, really good because if you don't know how it works, then you don't know if it's working, right? You understand? And what's the next thing? Number two, Randy? Well, if you know how it works, the next thing you need to do is once you get it, huh? No. And I've been troubleshooting. I got into this in 1971, so I've been troubleshooting a long time. And I found out that a lot of times somebody will call in and say something's not working, and you go out there. Yeah, that's exactly right. Verify the problem. I think I told y'all the story. I worked on computers. Got a call from Hartzell. A lady up there working said, "My monitor, this poor little thing's broke," is what she said. And I went up there and somebody had turned the intensity down on the display, so there wasn't anything wrong with it. So what did I do? I verified the problem. So usually when you see me sit in front of a monitor and it's not working, I'll pop it up and see if somebody's been screwing around with the contrast or the brightness. Verify the problem. And what's the next thing you do? Sometimes you can do this visually, but the next thing you do is you look things over. You just look things over. You'll be surprised how many things you can fix by looking things over. Yeah, so you got a lot. In the industry, it's very, very popular putting lights over everything. A lot of times you just go over there and you can look at the lights and see what's going on, and you can see what's wrong just by looking things over. Then the next thing, check the source voltage. Make sure you got voltage there, right? And then you actually start. That's the base. Then you start troubleshooting. But the problem is, or trying to make measurements inside the circuit. But the primary thing, number one, is you got to understand how it works. If you don't know what to expect when you put a meter in a circuit, don't put your meter in a circuit. So don't put your meter in a circuit to see what's there. You put your meter in the circuit to verify what's there, right? You understand that? So this is a bad diode, so I got another one up here, but this will be a good one I can put somewhere for y'all to troubleshoot. when you check diodes. I think we've got that in fact. Okay, so I'm going to change this over to a full wave. What should we expect out? So full wave center tap. So what is a full wave center tap? First of all, we're going to go over to a center tap transformer. So this is what we call a tap transformer. You can get them with two different types of taps. And this is what's on your power pole out there, or if you got a power pole. So this is a center tap transformer. And what we're going to do is we're going to use the center tap as a common. And then we're going to come over here and we're going to put two diodes right here. And then we're going to put our load right there. And the turns ratio is 8.75 to 1. And got one you need to look on with somebody so we can explain this. So so look down at the bottom. And I just realized this, guys. I've been teaching this for years, but this is really neat. This is the first book that I ever brought this up. But they're talking about the factor between the output, between the DC average of an alternation. And they're calling it the average. Now this is what sets the output, right? The DC average of an alternation. The DC average of an alternation is equal to V peak times 0.637. And this is over V peak. So the way we calculate V peak is we divide by 0.707. Now, what they've done to make it, hopefully you see what they've done. What they've done is they've multiplied both of them by 10. If you multiply both of them by 10, you get the same answer as if you don't multiply by 10, right? But these are the numbers we taught. So what they're saying is that, okay, I can take this factor between my DC average of my output and my peak value of my input, and we can come up with this factor, and this comes up to be 0.9. Now, this is really, really interesting. So what they're saying, once I know the factor, so this is the ratio between the output and the input. So what they're saying is I can take the RMS value. So what we've been doing is taking the RMS value divided by 0.707, then multiplying that times 2V peak over the pi. Well, what they've done right here is they put it in one formula. The only thing that they totally ignored is the diode drop, the drop of the diode. So it means this answer right here will always be bigger than what you will measure. So what they're saying is that if I've got 6.3 volts on my if I got 6.3 volts on my primary, then my DC average would be equal to 6.3 times 0.9. What does that give us? And this is a pretty neat equation, but what are they ignoring? they're ignoring the drop of the diode. So what's going to happen? I couldn't figure that out, how to get it right. So this answer is always going to be higher than what we actually measured. So what do we got? So I'm going to put this formula on the formula sheet. But this is a real good approximation. Approximation means what we're trying to do is we're trying to figure out if the power supply is working or if the power supply is not working. Right? You understand that? And if I know what the voltage is, it's going to be about this, then that's pretty neat. And especially if I know it's going to be slightly less than this, that makes it even better, right? So what do we got? 5.6. Now what this does though is this basically ignores the diode drop, right? You understand? And of course, so this is what I got my meter up here. And this is really interesting. And then I'm going to take my meter and I got it on DC volts. And let's see how we got. So what did we calculate the other way? Using all the math, we calculated 5.8 volts. Here we're saying we're going to get 5.6. Look at that. There's only 200 millivolts difference between this approximation and what we calculated. Another problem we have, of course, is that when we say 6.3 volts, is the transformer going to give me 6.3 volts? No. It's usually going to be greater than that. This is a 1 amp transformer, so what that means, and we're not getting we're getting 90 milliamps out of it, or I'm sorry, 9 milliamps out of it, right? I'm sorry, we're getting 18 milliamps out of it because we doubled the voltage. And, so we're not loading the transformer near its rated current. I'm just going to come up here and measure the output. And it's measuring 5.85 volts. So my output is measuring more, and of course, why is it measuring more? Because when I look at the AC output of my transformer, instead of being 6.3, it's actually 7.2. So it's actually more than what we've got. So it's about 900 millivolts more than what we got. I think that's pretty neat. Can you see how they did that? And guys, that's fine with me. That's a good formula. I didn't know that. I'm going to put that on my formula sheet. But when he showed me the math, it says, good gracious, that makes all the sense in the world. But your answer is going, if you do this on a test and you show your work, remember your answer is going to be bigger than what it actually is going to be. Because what are we ignoring here? We're ignoring the diode drop, right? Don't understand that. But it's really neat, really close. So we could do that on our, would you see where the 9/10 came from? Isn't that neat? So basically we're converting it to peak and converting it over to, by the way, what would a half wave rectifier be? Well, a half wave, since we lose that half cycle, what you would do is you would take that answer right there and you divide it by 2. And you'd come up and be a half wave. Do you understand why? Because this would be the average if you're getting both alternations. On a half wave, we're getting half the alternation. We're getting a 0 the other one. So if you divide that by 2, it should come up to be what we got a while ago. So let me erase that. And the next one, it would cause a pretty good error. So if you want to use that, that's fine. It's not on the formula sheet. I'll try to get, if I got room to put it on there. That formula sheet is pretty packed. Say we can go directly to but this is an approximation. And what's nice about approximation is if I go there and I measure 0 volts, we got a problem. If I go there and measure 3 volts, I got a problem, right? You understand? I know something's going on. Either the transformers lost some coils, which happens a lot. These coils, I don't know if you know, to get an extremely good magnetic coupling, the further we get the coils away from each other, the worse the magnetic coupling between the coils. So what they do, the insulation and they call it magnetic wire. The insulation on magnetic wire, you can hear them humming. They'll probably go out there by your transformer on your power pole out there. You hear that sucker hum, 60 cycles. Because why? I mean, so this guy's putting a positive and it's generating a magnetic field that's in the same direction. And like magnetic fields try to do what? They repel each other. So those wires are constantly trying to spread apart. That's why they put them on there real tight. And a lot of times your industrial transformers, they'll dip the whole transformer in wax to try to seal those wires in there and then keep them from moving. Because if they sit in there and they vibrate, what's eventually going to do? It's going to wear that little thing out. So that's one of the biggest problems we have with transformers is that you have winding short. If you have winding short, then you lose the turns ratio of the transformer changes, right? You understand that? So if they short in the secondary, that means we get less turns in the secondary, so you won't get near as much voltage out of it. And of course, you know, there's not really much you can do except take the dang thing apart. It's not easy to break that E apart, you know, rewire it. So normally we consider transformers to be consumable. We don't repair them. So this is why Alabama Power don't like to use three-phase transformers. They like to use 3 individual transformers. So it's more to install, but if one of them repairs, they're not replacing a 3-phase transformer, they're replacing a single-phase transformer that's wired to 3-phase. So if you ever get to a building, it's up on the power poles, it's going to be 3-phase transformers. If it's a customer's, I mean, it's going to be 3 single-phase transformers wired as 3-phase. But if you get into the commercial building, odds are it's going to be a single 3-phase transformer. Their transformer. So it depends on who the transformer belongs to. So that's a pretty neat thing, right? So just take VRMS and multiply it by 0.9, and that'll do a lot of the math for you. Now all they did in the book, for some reason, why they did it that I don't know, is they multiplied these numbers by 10. I guess they figured that we couldn't divide fractions. I don't know. But if you multiply both of them by 10, you come up and get what? You get the same answer. You'll see what they did. You'll see where that's at. And they rounded a little too much. But that's where those numbers came from. Another thing you got to be leery about, guys, is that sometimes they'll come up and do this. No, not on this one. Sorry. Let's look at our next one. And these will be the 3 rectifiers, and then we can give out a worksheet for class, and then we'll go lab. I'm going to draw it the way a lot of people draw it. This is the way it's drawn in the book, and then I'll show you an easier way to draw it, and you'll see it drawn both ways. We're going to use a center tap transformer, but let me show you. I'm going to just go ahead and get rid of it. And this is one of the advantages of this one. It does not require a center tap transformer. And diodes are a lot cheaper than center tap transformers. So what we're going to do is we're going to set up something we call a bridge rectifier. There was a development, and they drew it like this. And now these are resistors. And let me do this right. And this is how this got its name. But we're not going to draw it like this because it's not easy. So what I'm going to do is I'm just going to go ahead and draw a diamond. And then what we'll do is we'll just put a resistor in each leg. And this was named after the guy that figured it out. His name was Wheatstone, and then they picked up the name bridge. So now, no matter if we put anything in a triangle, we call it a bridge. So this is called a bridge rectifier, and this is very important too. In sensors, you're definitely going, if you take sensors class, and everybody, that's one of your requirements now. You'll learn about the bridge because this is one of the main ways that we sense analog sensors. So what I'm going to do is I'm going to come up here and I'm going to draw this bridge, and I'm going to draw it bigger than so I can draw it. And then I'm going to put one in the transformer at the top of the bridge, and we're going to put a dot there indicating about a connection. Then what am I going to do is I'm going to come up here, and I'm going to come up here, I'm going to put an anode. So let's do it this way. I'm going to put an anode, and over here I'm going to put a cathode. And down here we're going to do the same thing. And over here I'm going to put a cathode. So my AC sees an anode and a cathode. Notice this guy here has common cathodes, this over here has common anodes. And then what I'm going to do is I'm going to come over here and I'm going to put my load right here. So we never ever ground on a full wave bridge. We do not ground the center. In fact, it's designed to be run off a transformer that does not require a center. So we're going to cover right now. We're going to put our load right here. And what we do, of course, down here, this would be the common of the circuit right here. Or if it was grounded, this is where your ground would have to be right there. So I'm going to draw it as a common. So what we're trying to do is we're trying to figure out, now to figure out if this is a negative and a positive supply, we look at the lead that's not common, and then I follow back this, and notice both sides is pointing back to the source is the anode, so this is a positive supply. So let's see how this works. We'll start off with our first polarity. We'll say this side of the transformer is positive, this side's negative. That's going to put a positive right there on the cathode. So what would this diode right here be? A positive on the cathode, what would it be? Would it be on or would it be off? A positive on the cathode, would it be on or would it be off? It'd be off, good. This has got a positive on the anode, so this guy right here is going to be on, and we'll trace it through the rest of the way. Now when I come down through here and look at this one, this puts a negative on the anode, so this guy right here is going to be off. On the anode. This puts a negative on the cathode, so this guy right here is going to turn on. You see that? So current is going to leave the negative side of the transformer. It's going to come through here. Why ain't it going to go this way? Because this guy's turned off. It's an open switch, right? So it's going to go this way. It's going to go out our common lead. It's going to come up here. It's going to come up this way. That's going to make this side of the resistor negative. It's going to come up here and go that way. Why is it not going to go down? Because it's off, right? You understand? And plus, it's not looking for it. Negatives don't look for negatives. Negatives are looking for positives. So it's going to flow this way. It's going to go through this diode. It's going to go back. And okay, we're okay. How many diodes did it go through? 2. How much voltage are we going to lose on V peak out? We're going to lose 1.4 volts because they're in series with each other, right? You understand? Everybody okay? So let's change our polarities. Oops, I erased the wrong thing. I'll draw it back over. Okay, so now what we're going to do is we're going to come down here and make this guy right here negative. So this is negative, this is positive. So I'll bring over here and bring this negative. That's going to turn this guy here off. That's going to turn this guy here on. This positive down here is going to turn this guy here off. That's going to turn this guy right here on. Okay, so the other set turns on. Everybody follow this so far? Lost anybody? So current leaves a negative. Hits that point right there. Which way is it going to go? It's going to go this way, right? It's not going to go that way because this guy's turned off. It's going to go this way. Come up here, go through here. We're tracing from negative to positive. This is still negative, which makes that positive. It's going to go back here, and it's going to go down and go back to this direction right now. Now, of course, the advantage of this guy is that it does not require a center tap transformer. Center tap transformers cost a lot of money relative to diodes. Diodes are cheap relative to center tap transformers. But your common is picked up on the other side of, and we can, the negative supply just comes, so to figure out if it's a positive supply, we said if the anodes point toward the source, it's a positive supply. If the cathode points toward the source, it's a negative supply. So what we're looking at is we're looking at this lead right here that is not the common lead. And I look at these two diodes, and their anode is pointing back toward the source, so that means this is a positive supply. The other two diodes are just basically in the return side, right? Are you okay? And we call this a what? We call this a full wave bridge. This is so dang, well, if I use the same circuit over and over and over and over again, then sooner or later they're going to integrate this, right? To understand what integration is. That's when we take multiple solid state devices and we put them on a single silicon wafer. So we can buy these. I've seen these where they got three legs, and they come up here and they got this diode symbol right there. Well, that would be a diode that I would use in a full wave center tap, right? But it's in one package. So instead of me having two diodes, so this would be cheaper to buy, but it would cost more to repair. But when I'm engineering something and building them and selling them, I'm trying to sell them. I'm not selling them for the cost of repair. I'm selling them for the cost of selling, right? Y'all understand what we're saying? So you're going to see a lot of these integrated circuits, these rectifiers, you're going to see a lot of those in power supplies. You very seldom see individual diodes anymore. You'll see these, and we'll show y'all some. The ones we've got, it's got 4 leads coming out of it, and two of them's marked AC, and then one of them's labeled plus and one of them's labeled minus. And of course, what are you going to check these with? You're going to check these with an ohm meter too, right? We call it an ohm meter, even though your meter's measuring a voltage. Y'all understand that? Because it just don't translate it. So if this will focus in. So on this one, these two leads in the center, this is where you put your AC, and this would be plus, this would be minus. Now, it don't mean this. So if I wanted a minus power supply, I'd use this one to the top of my load, and I'd use this as my common. If I wanted a positive power supply, then I would hook my minus to common, and then this would be your power supply thing. So this guy here, basically, you can get whatever type of power supply you want out of it, right? Either negative or positive. But sometimes you see the 4 diodes too, so it all depends. So these would be cheaper to buy and install, but it would cost more to replace, right? You understand? The 4 diodes would be cost more to install, but it would be cheaper to replace if only one of your diodes went out. So if one of your diodes went out, you'd replace this whole thing. And like I said, why do you see so many of these things? Is because when they make something, they're not looking at the cost of repair. They're looking at how much they can make when they sell that thing, right? So they're trying to make it as cheap as they possibly can. So they're going to use a lot of integrated devices if they're available. Thank goodness for integrated circuits. So let's calculate this one. Let's just come up with a division ratio. So don't use the actual one. No, we do, but we'll do that in a minute. So let's say we got 120 votes, even though here we got maybe, what, 112? And then what ratio do y'all, we'll use the 4-to-1. What would be my DC output? My approximate DC output? So I'm gonna wire up a bridge real quick. I think I got enough diodes here. One of mine is bad. Yeah, I got 4. My bad one over there. Oops. So we'll make a positive supply to start off with. Hey, where's my feeder wire? It's not good. We'll use both methods and see how we do. Brian's not here tonight. I knew somebody. It's gonna take me a while. Brian, but he told me he wasn't gonna make it tonight. Okay, guys. So what do we got? What you got, Brandy? 26.5 volts. What you got, Courtney? What's that? 15. What you got, Kareem? What's that? 16.8. What you got, Scott? 24.6. What you got, Charles? 13.07 or 13.1. More Brandon. Okay. So let's see. First thing I need to do is I need to calculate the turns ratio, right? So I'm going to say my V secondary is going to be equal to 120 divided by 4. What do we got? What's that? 30 bucks. Okay. Then what's the next thing I need to do? I need to calculate the peak secondary. So it's going to be 30 divided by 0.707. What do we got? What's that? 42.42? this is V peak. Then I'm going to calculate V peak out. This is going to be 42.4 minus 1.4. Why 1.4? Because it goes through 2 diodes, right? 2 diodes every time. What we got? That's okay. What do you got? No, 1.4. 42.4 minus 1.4. Yeah, that's that you do it. And then we calculate volts DC. You know, volts DC is going to be equal to 41 divided by 3.14 times 2, because it's full wave. So what does that give us? $20-something volts. Times 2. 26 volts. So everybody see where they made mistakes at. Let's try that other method. So I'm going to take 30, and I'm going to multiply that by 0.9, 27 volts. Close, right? Ain't that neat? That's what I understand. So that's a good way to check your answer. Yeah, well, you have to use what's over here, not what's over there. This is what, so you'd say 30. So volts DC is going to be equal to approximately 30 times 0.9, and I came up and got 27 volts. But it's actually 26. Now here we had a pretty good difference between this, because here we lose 2 diodes, right? You understand? The other one we're only using 1 diode. But if it's multiple choice, it ought to be this ought to give you a close enough answer, so you'll probably get it. But you know it's going to be what? It's going to be less. It's not going to be rounded down. It's going to be less. So you don't know exactly what it's going to be. 26 volts, so that's a whole volt difference. So that's pretty neat, guys. That knocks off a ton of math to get us about where we need to do. But remember, the first thing you're going to have to do is calculate this voltage over here. Don't use that voltage right there. This voltage right here is not what's setting the output voltage. It's the secondary voltage that's setting the output voltage. It's just 120 volts. It's not setting our output voltage. It's this voltage right here that's setting our output voltage. It's the secondary voltage that sets the output voltage. So the first thing we need to do before we can even use this formula right here is we need to know the RMS secondary voltage. But what's nice about this is that in this formula we can use what? We can use RMS. So that saves a ton of math. Look at this. So we did all that to come up and get what? 26. What's that? 26.1 volt. We did this and came up and got 27. Now, what's the difference? Why is it wrong? Well, it's wrong because this formula right here does not compensate for the diode drop. You can't take out 1.7. You can't take out 1.4 volts because it's an average, right? You understand that? We're going from an RMS. The other one, we're taking out 1.4 volts from VP. But this is not VP. We're dealing with RMS. And I can't figure out the actual fraction. It seems like it's like 0.8 or something like that. Pretty close to it. But, to get the exact answer, but the problem we got, guys, is this is not going to be the exact answer, right? You understand? So when we use that 120, if we're we're using 120. So under 120 is what National Electrical Code calls the nominal voltage. And then they say, well, legally it could be 120 plus minus 10%. So legally it could be, around 100 volts, but it could be up here. And according to National Electrical Code, that would still be legal for what Alabama Power is giving you. So that means you can measure this voltage at your house, and it'll be one thing. You could go, if they're on a different transformer, you could go to your mother's house and measure it, and they'll have a different voltage. Because NEC can't say exactly what voltage you have. Because when Alabama Power generates voltage, it's regulated when they generate it, but they have to send it over all them wires, right? You understand that? And then they compensate it with tap transformers. So they try to compensate with tap transformers, but they can't have an infinite number of taps to give you exactly, 240 and 120. But so that's what the National Electrical Code is. This transformer says 110, I think. This transformer says 120. This transformer says 110. Which one's right? You look at a light bulb, most single-definite light bulbs are set for 115 volts. Who's right? They all are. Right? Odds are you're not going to get any of those anyway. Here I think we've got 112 volts here, which is still within perfect limits of what the National Electrical Code says is legal. So this is why when we give these calculations, we're going to give you 120 volts is what we use most of the time. Of course, because that's what National Electrical Code says is the nominal voltage. And that's what they use all through their whole thing, 120 volts and 240 for residential wire. So it looks to me, this math right here is great, but it looks like to me that this right here would be close enough to troubleshoot. So if I calculate 27 volts and I go in there and I measure 25 volts, is that okay? Sure, that's okay. I go in there and measure 28 or 29 volts, is that okay? Sure, that's okay. I go in there and measure 15 volts, then something's wrong somewhere. Either one of our diodes open. So one of our diodes open, what happens to our power supply if one of the diodes open? Well, we turn into a half-wave rectifier minus 1.4 volts. That means if you lose one of these diodes, your voltage drops way down. But if I don't know that, if I'm just measuring to see what's there, and I get in here and I measure 13 volts, and I don't know it's supposed to be 26, 27 volts, then I say, well, power supply is good, right? You understand? Because all you're looking for is getting something out of it, and you're not seeing what the voltage is supposed to do. Now this is the math that we use for unfiltered power supplies. As soon as I add that filter, this math is gone. And the other one, filtered power supplies are easy. So if you want to use 0.9, that's okay. It probably won't be on your formula sheet unless I can find a place to put it. But y'all see where the 0.9 came from. It's pretty neat. They just took the RMS value and divided it by, the average value of an alternation. And then they divided it by what we do to convert it into VT. 707 is pretty. What ain't that neat? Huh? On the secondary by 0.707. That gives us this. Yeah, VP out. This would be out. This is where this formula loses it. This formula right here does not compensate for the drop of the diode. Yeah, 1.4 because every path we go. So when it goes this path, it goes through two diodes, right? And they're in series with each other. And we learned that voltage drops that are in series, we add them together. We learned that in DC. right? You understand that? So that means each one of them dropping 7/10 of a vote. We go through 2 of them, so that means they're going to drop about 1.4 votes. And notice I said 1.4. We use what we call second approximation anyway, because the diode drop varies a little bit over when it turns on and when it actually, and it varies the more current flow you put through it. I think the 914 can always, when you run 1 amp through it, it could actually drop up to 1.1 volt. But still 7/10 is okay, right? Because good gracious, what's the difference between 1.1 and 7/10 of a volt? 400 millivolts. 400 millivolts is not that much. So instead of me trying to figure out the exact drop across a diode, we use 7/10 for a silicon, and we call that the second approximation. If I'm putting 200 volts on the dang thing, I don't even take out the 7/10 of a volt anymore, because that would be just ridiculous to do that. So usually anything above 100 volts, we leave off we forget about the 7/10, and we use what we call ideal approximation. And we don't ever, you use third approximation if you're an engineer, if it means anything. Very few engineers don't do that, because what we're dealing with in electronics is we're dealing with so many different things that have tolerances on them, right? You understand that? So our resistors have tolerances, our diodes has tolerances. They usually don't give plus or minus, they'll give you a minimum. When you look at a lot of these data sheets, they give you a minimum and a maximum. And what are they telling you? They're telling you the tolerance, which means it's going to be somewhere, but it probably will never be the maximum, and it'll probably never be the minimum. It should operate somewhere between. When we start looking at, we got a rating for a transistor that's beta, which is the gain of the thing. The minimum is like 30, and the maximum is like 110. So we're talking about a huge tolerance, right? All you got to do is, for half wave, what would you do with this? You would divide it by what? 2. You divide your answer by 2. For full wave, what you can do is just multiply it by 0.9. And that's going to be close enough for what? For troubleshooting. Which is pretty neat, guys. Like I said, I was looking at that in the book. They kept saying 90%, 90%. I said, what? How in the world did they get 90%? When I've been using this math right here all along, and then when they explained it to me, how they combined this formula with this formula. That's what they did. They combined that formula with that formula. That's all they did. So they took this formula right here, and they combined it with that formula right there. Which is really, really neat. And they came up and got 0.9. But all that formula does is ignore the what? Diode drop. So when you're taking a test, if you use that formula, you got to remember the right answer is going to be less. But not much. It's going to be less. But it should be close enough for you to what? For you to figure out which one's the right answer. And it's definitely good for troubleshooting. So all I got to know is what the transformer's rated here, what the division ratio is. And by the way, a lot of transformers don't even give you the division ratio. It gives you an input voltage and an output voltage. What you got to understand is if you don't use those voltages, you're going to have to know the division ratio. And I've seen that done a lot of times. So they might say, okay, if I put 440 on the input, I get 120 out. Well, see, that would be a divide by 4. So I can get the ratio, that's a divide by 4. And that means, okay, what would I get if I put 24 volts on that? Well, I'd get 6 volts out, right? Y'all understand that? So sometimes transformers don't give you the division ratio. They give you a input voltage, and they give you a output voltage, right? And then you can calculate the turns ratio. And then if you know the turns ratio of the transformer, you can do what? You can hook it up to anything you want. And then you get what you need out. And this happens sometimes. So this is a full wave bridge. The other way you could draw it, guys, and this is the easiest way to draw it. And I got one more thing to show you, and then we'll go to the lab. We got time. So we'll solve for ours. So the easiest way to draw this and to figure it out is I'm gonna come up here and I'm gonna put two straight lines. And I want a positive supply, so what I'm gonna do is I'm gonna start up here, and notice here I don't have to figure out which way they go, I just point them in the same direction. And then my DC is gonna be right here. And then I'll bring my AC in right here. That's a full wave bridge. If you look at it, it's exactly the same circuit, but this is the easiest way to draw it. If I come up here and make this common, so that, and what's nice about the bridge, it don't care, since the common is on the other side of the bridge, you determine which one's common. So if I wanted a positive power supply, I would make this one common. Of course, this would be normally drawn upside down, because normally we put our common on the bottom. And if I wanted a positive power supply, I would come up here and put my common down there. So what's nice about this is that on the output of that thing, you determine what's common. That makes sense? So this is the full wave bridge. Another thing that you're going to run into, and you got to look for this, is we've got a lot of plus and minus supplies out there. So what they'll do is they'll come up here and do this to you. So I'm going to draw the bridge again. Okay, and we're going to make a positive supply. So what I'm going to do is I'm going to put two anodes toward my source. And then over here, I'll put cathodes. And then my AC comes in on the top. Now notice what I used. What's this? Well, first of all, what you need to look at is you need to see that center tap. Full wave bridges don't use center taps. This is a full wave center tap, but it's two. If you look at this one, the anodes are pointing toward the source. If you look at this one, the cathode's pointing on the source. So this would be negative positive, this would be positive negative. So what you got is it's using a bridge rectifier, but it's using it for a full wave center tap. This is what the trainer uses. That's what they use inside this thing right here. I guarantee this is what they probably use in your stereo out there. And what you got to see is you got to see that the common is not over here. The common is not one of these. Your common is right there. So if you see that, this is not a full wave bridge rectifier. This is two full wave bridge. These are two full wave center taps, but it's using a bridge rectifier because they can use what? They can use one of these. Everybody understand that? But the problem is people will see that and they'll say, well, that's a full wave bridge, but it's not. It's just a negative and positive supply. So what we need to do is look at and see the I've got this in a PowerPoint somewhere. It's probably this is the little book that comes with the trainer. And what's nice a lot about people that sell electronic stuff is they give you the schematics on it. So here's the power supply. So that transformer has three. It's a multi-tap transformer. Two of them are center tap. This one right here is not center tap. But notice what they do with this center tap right here. They take it to a what? They take it to ground. See that? And then this is an internal, and here's my what? There's my bridge rectifier. But this goes to a negative supply, and then this right here, let me make sure. So this is the positive supply, and this down here is the what? Is the negative supply. These are the voltage regulators. This is a 7812, so this is a positive 12 volt regulator. This is a 7912, so it's a negative regulator. This is a fixed regulator. This right here is the 5 volt regulator. So that's where the plus 5 volts come up from. And here's your variable supplies out here. We'll talk about, these are your variable regulators right here. So these are the ones that you can adjust. Okay. And we'll take, and later on we'll come up here and we'll take this thing apart and we're going to look at it. But here's the power supplies that's available. So this is ground, and it's ground. We have a minus 12, we have a plus 12, we have a plus 5. So these are what we call fixed regulators. That means these guys, you can't vary them. Then right here, we have a plus V, and we have a minus V. Then it says these are what? These are adjustable. Okay. And of course, we have these two knobs down here at the bottom. And this is where you adjust your positive power supply, which changes the voltage on this guy. This is where you adjust your negative supply, which changes the voltage on this guy. Okay, you understand that? So we have fixed regulators, mean these guys right here do the same. And so if I wanted to get, if I wanted to measure the voltage on this minus supply, then I would go between the black one, which is ground, and this is grounded, guys, so it's grounded to the power cord. And then I would just, there's 5 volts right there. So this is the one that we're using in the first lab. So we're using ground and 5 volts, and then we're going to connect it up to a potentiometer, right? So that way we can get any voltage, because we got to start out across our diode at what, 450 millivolts or something like that. So most of y'all had y'all's circuit hooked up okay when we left. And then we'll take that, we'll pop this thing apart, we'll look at the power supplies in here. And what's nice about these is they're easy, since they're linear power supplies, what advantage does those have over switching power supplies for us? Well, if they break, we fix them. These computers use switching power supplies. We had one go out on that trainer in the back there, and what did we do? Did we fix it? No, we replaced it. And why? Because switching power supplies are very efficient, but you can't hardly fix them. You could probably do what we call a shotgun. Y'all know what shotgun in troubleshooting is? Anybody heard that term? Shotgun means you just replace everything, which is a lot of your car repairs done like that now. They'll go up and hook it up to a computer. And it gives them 3 things that's bad, and what do? They replace all 3 of them. And odds are it's what? It's just one of them. Because that's what we call shotgunning. So shotgunning is you don't troubleshoot, you just replace them. I've seen people do that. They'll replace things one at a time. We had a company I worked for, it was a scale company, and they had computerized scales. And that's the way the technicians troubleshot it, is if the scale wasn't working, they would just start swapping parts. And they had drawers of parts, and they just started swapping parts. And they'd swap it. If it didn't fix it, they'd put it back in the good parts bin. And then they'd swap it. If it didn't fix it, they'd put it in the good parts bin. And then swapping it, it fixed it, and they would throw this part away. What I got there, and then after that, after a while, they couldn't hardly fix anything because they ended up with so many bad parts in their, what they call their good parts. Because that's the way they troubleshoot. So when I got there, I figured out all the bad parts, and then I did troubleshooting, and it was a big difference. Well, I didn't swap out parts. I knew what parts was bad before I changed them out. That guy thought I was something, but I was just doing. Oh yeah, he'd brag about me all day. So, but yeah, so we fixed. Well, I could probably still work for that guy. Working on scales is the bad business. It's almost as bad as roofing. Anybody ever roofed before? It's something you don't want to do. All right, guys, let's go ahead and we got gracious. We don't have time to go away. We don't have an hour. What we'll do next class is we'll just come in and we'll start off in lab. Let's start looking a little bit at when we start filtering these things. So let's calculate, first of all, let's calculate what we have, what the circuit that we actually have. Yeah, you have to take it back. And I'll draw it up here. We're solving for this guy right here. So we have a transformer, it's got 8.75 to 1 ratio on it. Got 120 volts applied. What we're trying to do is trying to figure out what the voltage across the load is, what the current in the load is, what the power is required by the load, and then we want to calculate the primary power and the primary current. That's what this is. So, get it right in a minute. Keep trying to sell primary. Should we expect to cross load? $11.4. So let's write them down here first. 11.4. I think I gave y'all the turns ratio wrong, guys. That's not right. I gave y'all for half of it. It's supposed to be twice that. We got 120 in, 12.6 out. That's still not gonna work out. 9.5. Let's try it with 9.5. So it's 120 divided by 9.5. Hmm. 10, if you go the long ride, it comes up to be 10.5 volts. Still not bad, is it? Something's going on here. I gotta figure out what's going on. Oh, I know what's going on. I was using the center tap instead of the outside. Okay. So what should our current be? So 11 volts, 11 point something volt, 11.5 volts. What's that? 0.4. So see, I knew I had a problem. So I was measuring half of that. And when it fell off the table, I hooked it back up. I used the center tap instead of it. But see, real fast. What side of the load? This 1K, I forgot to give y'all that. So that's 11.4 milliamps. What's nice about 1K, and we'll use this a lot, 1K is 1 milliamp per volt. Y'all can do the math. So it's going to be divided by 1,000, right? So what would our power be? Power of the load. You can use V times I, or you can use V square over the R, or you can use I square R. It doesn't make any difference. What power do we have in the load? Come on, guys. These are formulas you should know. Not look up on a formula sheet. They're not on Ohm's law and Watt's law is not on your formula sheet. And why not? Huh? Yeah, there's certain things you should know. You know, that would be like trying to use the book you get to study for your driver's test while you're driving. So what's the power in the load? 130 watts. No, it can't be 130 watts. That'd be milliwatts. Maybe 130 watts. This dang thing would be burning up here. So if you're saying I'm taking 11.4 and multiplying it by 11.4 milli, and I'm getting 130. So what is that? Might be 130 milliwatts. Milliwatts. Did y'all say that? I just didn't hear it. Okay. Okay, so what's the power in the transformer? What's the power in the primary? Take a guess. What's the power in the primary? What's the power in the primary? The same. It's the transformer don't change power. So what's okay? So it's 130 milliwatts. It'll be a little higher because the transformers. Okay. So what's the current in the primary? So how did you get that? So did you take 130 and divide it by 120? So current is P over V, right? That's one of your formulas. P over V, that's a big formula right there. So what have we got in our primary? I'm listening. 130 milli, excuse me, that's very important. 130 milli divided by 120. So how much current do we have flowing in our primary? Yeah, that sounds right. So look, 1.1 milliamps in the primary to get 130 to get 11.4 milliamps on the secondary, but you got to understand that's it, Danny. That's what a transformer does. A transformer does not change the power; it changes the current. How much work are we paying for? Are we paying for 1.1 milliamp? No, we're paying for 130 watts. If your transformers were 100% efficient, up there in TVA, they would be providing 130 milliwatts of this thing right here. Now they're not, but they're pretty dang close. So let's look at the circuit real quick. So how do you calculate the current in the primary? You just take the power in the load and divide that by the primary voltage, and that's going to give you the primary current. Now, what are we going to fuse it at? We're not going to fuse it at 1.1 milliamps, right? You understand? NC, I think NEC, and I need to know this guy, but I think if it's below certain voltage, you'd multiply that by 3, you'd increase it by 300%. We'll talk about why in power supply. Okay, guys, let's see what we got. First of all, let's look at the circuit. So it's not drawn like a bridge. So here's the circuit. So those diodes are not parallel. So if you look at the center, I've got these two diodes in the same vertical line. I got these two in a different vertical line, but they're in the same vertical line. So these are not connected together. This is where my AC comes in. Here's my common anodes. Here's my common anodes right here. I mean, here's my anodes. So that puts this part of the resistors positive. Then I had to put a wire to come around to the other side. There's my negative. So there's my circuit. And even though they look like they're in parallel, they're not, right? You understand? So a lot of people see things side to side, and they say they're in parallel, and they don't look to see if the ends connect together. So the top and the bottom have to connect together to be parallel, right? Okay, so there's our circuit. And we should expect around 11 volts. Did y'all use the whole calculated out, or did y'all use the 0.9? You did all of it? So here's what we're measuring. I got my meter. By the way, on a bridge, it makes no difference. It depends on what you consider to be common. So if I consider if I consider this to be the common, then it measures a minus voltage. If I consider this to be a common, it measures a positive. So 11.75 volts. Not too bad. Not too shabby. It's not too bad. And, what did we get when we did the 90%? Yeah, 12. And why? So it's still not bad because, 11.5 is what we calculated. We did 90%. We came up and got 12 point something. So, it's probably still less than a vote, wasn't it? It's pretty neat. So approximation, just for a basic approximation, and use 0.9. That's what I would do. If it's half wave, you take your answer and divide it by what? By 2. And it should be close enough for you to see if the power supply is working or if the power supply is not working. Now these are unregulated, unfiltered power supplies. As soon as we add that filter, that 0.9 is gone, all this is gone. Y'all understand that? Because it never comes to ground. The DC average of an alternation is gone. Because we're not going to use an alternation anymore. We're going to get DC out of this. And it's not that much harder to it's not real hard to calculate. In fact, to me, filtered power supplies are easier to calculate. But not since I just learned the 0.9. The 0.9 makes these guys pretty easy. Okay, any questions? So what we have here, this is due next class. There's also an assignment due, I think, next class. What was the assignment? Assignment 3, I think you all do. I think it's like I think the first few assignments, I can't remember how many assignments they're basically doing one assignment. So, any questions?